talking about classifying functions as even or odd. But basically, if you think about the parent function as being multiplied by -1, you're thinking about all of the y values from the parent function being multiplied, like taking the opposite of those values in order to have the same x values as the parent function. So it ends up reflecting all of the points across the x-axis versus if you're thinking about multiplying x by -1, then you think about reflecting across the y-axis because you're multiplying each of the x values by -1 in order to have the same y values as the parent function. To keep them straight, I always think about y equals to x squared, which I have graphed here. Right, y equals to x squared. So if we were thinking about applying a vertical reflection, we would have y equals to -x squared. And the reason that I like to use this as my reference is because I think you guys are so familiar with quadratics at this point. And you know, hey, the coefficient on x squared is negative. So that means that's a parabola that opens downward. But we could think about these points that lie on the parent function reflecting across the x-axis. So like 0, 0 goes nowhere, but 1, 1 is now at 1, -1, right? 2, 4 is now at 2, -4. -2, 4 is now at -2, -4. Versus if we think about a horizontal reflection being applied, our equation would be written like so. And that horizontal reflection would really not do anything to any of the points. Like 0, 0 wouldn't go anywhere. 1, 1 and -1, 1 would be just flip-flopping across the y-axis. So all of those points end up switching. And the graph still looks like y equals to x squared. And again, that's because y equals to x squared is an even function. So even, therefore, the graph does not change. Using that as a reference. We already did the graph of cube root of x earlier in this lesson, so why don't we change this to be the square root? Just get rid of the little 3 there next to the radical. So let's think about coming up with the equation of the square root of x reflected about the x-axis. So we're coming up with the equation of a new function, so we could use a new function name, like I could use h of x. And how would I write the equation for the square root of x being reflected across the x-axis? Would an x-axis reflection be vertical or horizontal? It would be vertical, meaning we would write the equation as negative square root of x. Yeah, so anything vertical we think about as happening like to the outside of the parent function because it's happening to the y values. Anything horizontal is happening like to the inside of the function to all of the x values. And then reflected about the y-axis, which would correspond to a horizontal reflection, we can name, I don't know, called z of x. And what would that look like?
square root of negative x?
The square root of negative x. Are you getting like game ready right now, Reagan?
Yeah. Oh, so the hair's just fluffy with you. I got it.
Okay, multiple transformations happening. So thinking about reflected about the x-axis, we know what that looks like. Maybe I'll call this one m of x. Okay, so reflected about the x-axis, we said is negative root x, right? And then down 5 units indicates a minus 5. So negative square root of x, and then minus 5, so it's happening to the outside of the function because down 5 units indicates a vertical shift down 5. And then maybe p of x. So reflected about the y-axis, thinking about that as a horizontal reflection. Okay, anything horizontal, it kind of takes an extra second to think about, at least for me. So reflected about the y-axis, that's a horizontal reflection, so we would be thinking about the square root of x being multiplied by negative 1. However, there's also a horizontal shift to the left 3, so to indicate that,
It had to be plus.
right, and I would put the x plus 3 in parentheses. I'm okay with you giving the simplified version, like thinking about distributing that negative, but like you end up passing through this in your head still. And notice that all of these we're asking for an equation. So you have like your function name. You could even use y equals, but you have your function name equals. Making sure you're not just writing an expression. Make sure you're writing an equation. All right, any questions on any of those, you guys? Okay, let's kind of quickly go through actually graphing some of these. So square root of x, parent function. Right, this is our parent function. So why don't you guys go through and why don't you list what transformations are happening in order next to the function, and then go ahead and sketch its graph, and then we'll all check together. I'm gonna freeze this for a second. So graphing the parent function and thinking about those points that you would reference to take through the transformations. For C and D, be careful of identifying the horizontal shift. I use that color. Oops. Sorry, you guys, that probably took me longer than it should have. How's it going, you guys?
Almost done.
Almost done. Okay, we'll compare our graphs in a second here.
I've been done for a while.
Well,
Smarty pants. No, I just.
speedy.
We're on long.
Okay. Did you write down what transformations occurred too?
Yeah.
Okay. So why don't we all compare?
On C and D, I had some little Q's. Yes.
Yeah, you had to make sure. So C and D is the ones, because there is, anytime there's a horizontal shift and there's either a horizontal reflection or like today we'll talk about horizontal dilations, you need to think about factoring whatever that constant is out of the quantity. So you can see what the actual horizontal shift is. So B, vertical reflection, down 2, that one's pretty straightforward. H of x, you had to factor out that negative, so we think horizontal reflection and then write 3. J of x had a lot going on. Vertical reflection, then a horizontal reflection, left 1, up 4. Questions? We're okay with that? Cool.
Yeah. So basically,
We're cooking.
We can factor out the negative one to show that's a horizontal reflection.
Exactly, and then sometimes, like we're going to start talking about when there's vertical and horizontal stretch or shrink. So if x is being multiplied by anything besides 1, you have to think about factoring that out. Okay, so let's look at this equation, or not this equation, this isn't an equation, this is a graph. First of all, what would the parent function to this graph be? Yeah, it's absolute value.
Knock it. Boom.
Absolute value. So for figuring out what transformations are happening, and I should probably said transformations, not just translations, because we do have a reflection happening. So thinking about listing the transformations that would occur to the parent function in order to result in the given graph, well, it's pretty obvious that there's been a vertical reflection, right? Because the parent function normally opens upwards. So we can see that a vertical reflection happened, and we can interpret that as being the first transformation. So there was a vertical reflection. We have not yet talked about dilations, but if we think about the parent function, remember how I talked about thinking about y equals to x as almost being the parent function, and then thinking about absolute value as being a transformation itself? Do you remember me mentioning that? It's not that important for this, but, or you could just be like, hey, I know that for absolute value of x, we have the point 1, 1, 2, 2, 3, 3, 4, 4, and so on. Okay, and negative 1, 1, negative 2, 2, and so on. So we can see that, like, there has not been any sort of stretch, right? Like, to go from this sharp corner, we go to the right one, down 1, and we're at the next point. Like, there's a slope of 1 and negative 1 for each part of that V shape that the absolute value makes. So no dilation. And then we can think about, well, how did this point get from the origin to where it landed, right? It finished at 1, 3. So that means that the point that was at the origin, we would have done a vertical reflection 3, right one up 3. So why don't you guys take a second and see if you could come up with an equation that could represent this graph, taking into account those transformations. So you could name it something else. You could do y equals, but you're writing an equation.
Oh. Boom, indeed. Okay.
Would anybody like to share their equation? Regan.
Okay. Here's my little thinking. It's y equals negative absolute value sign number 1, x minus 1, absolute value sign number 2, plus 3. Are we cooking?
I agree.
We're good with that.
You cooked. You were not cooked, you cooked.
That's right.
I always, every year when I teach AP, I have like a way that I address them in emails all year long. And this year's group are the chefs because they're cooking. Last year was chat.
Chat?
Hey, chat. So like you look through every single email from last year's group, it always starts with like, hey, chat. Good morning, chat. Like this, that. Nobody ever says anything. It was more like it would bring myself joy. Like I'd have a little giggle about it whenever I would send out an email.
What's the word? It's like funny because you know it's not supposed to be funny, or no? How was it? It's like it's intentionally not funny to be funny, right?
Huh?
Do you understand? Like
No, I've been understanding for years.
I'm so stupid. I should have just said ironically. It's like It's like
Ironically.
yes, ironically.
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 It started because the seniors from last year told me to say to like that group that I had to say, hey chat, is this real? And so I did it randomly in class one day and they like all, oh my God, Josephine's face, like she cringed so bad. It was so funny. I was just like, oh God, I'm never saying that again. But then I started sending the emails with it and it just, their hey chat.
Just went out from there.
Their hey chat. Okay, anywho. So we've talked about shifts, reflections. So next we're getting into what I feel like people have the hardest time with, the dilations, like thinking about applying stretches and shrinks. But if you think about like shifts and reflections in terms of like if you're applying a horizontal shift to the right one, you're thinking about subtracting 1 from each x value in the parent function in order to have the same y value as the parent function. Like a vertical reflection, you're having to think about multiplying each y value from the parent function by -1 in order to have the same x value as the function. So anything vertical, you're thinking about applying to y in order to have the same x value as the parent function. Anything horizontal, you're having to think about doing something to x value of the parent function in order to have the same y value as the parent function. Also, something that's kind of cool, I think, about with dilation, so like the stretching and compressing, is at least with algebraic functions, you can oftentimes, like if you're just presented with a graph, you could interpret like a vertical stretch as being a horizontal compression, maybe not by the same factor, or you could interpret like a vertical compression by a horizontal, like as a horizontal stretch. What's I think interesting is like that's true for the algebraic functions, but like we're studying transformations with the functions that you guys are the most comfortable with at this point. those parent functions, like all the algebraic functions that are y equals to some rule that's just in terms of x, we're going to be able to like take this knowledge of transformations though, and then apply, like whenever we start studying exponential functions and logarithmic functions and the trig functions, like we will be able to think about those graphs from the same transformation perspective, like in the same way that we're thinking about applying transformations for these functions. So we want to get super familiar and comfortable with thinking about applying transformations to these algebraic functions so that then we can use those same skills and that same perspective with what we call the transcendental functions, the exponential, log, logistic, and trig functions. But what's kind of interesting is the algebraic functions, that can happen, where like a vertical stretch could be interpreted as a horizontal shrink, but that's not true when we look at the trig functions. Like that's not going to actually happen. It's just something that's kind of interesting. Okay, so vertical, stretch or compressing. I'm also, if you prefer to say shrink instead of compressing, I'm cool with that. But we're thinking about the parent function as being multiplied by a constant other than 1. And we're thinking about positive constants here because if we were thinking about a negative value, we would interpret that negative as being a reflection. Yeah, we've already talked about reflections. So if the parent function is being multiplied by a constant that's larger than 1, that means that you're thinking about each y value from the parent function being multiplied by that constant in order to have the same x value. So like multiplying y by 3 in order to have the same x value as the parent function. So if you're multiplying each y value from the parent function by 3, that's going to end up stretching the graph vertically, or visually it looks like it's stretching the graph vertically. Whereas if you're multiplying by a value that's between 0 and 1, that's actually going to result in a vertical compression. So like if we think of a value that's between 0 and 1, for example, 1/2, okay? So if you have the parent function being multiplied by 1/2, what's another way that you could interpret that? What's another way you could interpret multiplying by 1/2?
Oh, so, shrinking.
What operation? Yeah, dividing by 2, right? Like multiplying by 1/2 is the same as dividing by 2. So whenever we think about multiplying a parent function by a value that's between 0 and 1, we describe that as a vertical compression or a vertical shrink by a factor of whatever the reciprocal is. So in the case of the parent function being multiplied by 1/2, we would describe that as a vertical compression by a factor of 2. Because the compression is indicating that we are dividing each of the y values by 2. Do we follow that in order to have the same x value? And I think sometimes like the visual of it helps with that. Okay. Horizontal is the one. Anything horizontal I feel like takes an extra second to think about. So horizontal stretch, if x is being multiplied by a constant that's larger than 1, so like let's say that x is being multiplied by 2, you're having to think about doing the opposite operation, right? So like in the case of when we were thinking about shifting to the left 2, right? That would be represented as x plus 2. We were thinking about subtracting 2 from each x value to have the same y value. So in the case of x being multiplied by 2, we would be thinking about dividing each x from the parent function in order to have the same y value as the parent function, which results in a horizontal compression by a factor of whatever c is, so like by a factor of 2. Where if the constant that x is being multiplied by is a number between 0 and 1, so like 1/2, which could also be written as x over 2, you're having to think about multiplying each x value from the parent function by 2 in order to have the same y value as the parent function. So you would be thinking about horizontally stretching by a factor of whatever the reciprocal is, 1 over c. So in general, when you are describing what the dilation is, you'll be saying like a vertical stretch or a vertical shrink or a horizontal stretch or horizontal shrink by a factor of, and that factor is always going to be greater than 1. And remember how I said for shifts, like you don't have to say vertical shift up 3 or horizontal shift to the left 4. I'm okay with you just indicating the direction. For dilations, I am pretty particular about how I want you to describe it. So I want you to describe in this way. Does that make sense? So like by saying either stretch or compression and then by a factor of whatever that factor is, like you are indicating like, oh, I am stretching or compressing, I'm multiplying or dividing x or y depending on whether it's vertical or horizontal. Instead of drawing the graphs out, well actually maybe I'll draw it for a couple of these. But I was thinking it might be helpful to actually do in Desmos. But this is the line y equals to x, which we can think of as the parent function here. And like if I wrote out y equals, and in parentheses, put 2x, that's indicating that x is being multiplied by 2, versus if I were to write the equation, which would have the same graph, as y equals to 2x, like so, that would indicate that the parent function, like the y values are being multiplied by 2, the parent function. So in the first way that I wrote this, we would interpret the transformation as being a horizontal stretch or compression. Horizontal always takes an extra second. It's like the opposite of what you want it to be. Compression by a factor of 2. And the reason that happens is because we would be thinking about dividing each x on the parent function by 2 in order to have the same y value as the parent function. Okay, so like thinking about that, well, 0, 0, if we were to think about dividing the x coordinate by 2, like nothing's happening, right? But 1, 1, if we think about dividing x by 2 in order to have the same y value, this point that's at 1, 1 would be going to 1/2 1, exactly. And the point that's at 2, 2 would be going to
1. Wait, yeah, no, 1.
just taking, so the point 2, 2, think about dividing So we would be going to 1, 2. Here, I'll choose the even x value. So if we were at 4, 4, and we take the x value and divide it by 2 to have the same y value, we would land at 2, 4. The 0.66 would go to the 0.66 would go to 3, 6, right? Eight would go to 8 would go to 4, 8. And then you guys also, like 10, 10 would go to 5, 10. You guys also know what this graph looks like from like an algebra 1 perspective, right? Like y equals to 2x, you're like y equals mx plus b. The y-intercept is 0. The slope is 2. And if you look at this, this works out, right? Like we would go right 1 up 2, right 1 up 2, right 1 up 2. So it also makes sense with like our algebra 1 perspective of this graph. But you could think about like going into the negatives, like -2, -2, dividing -2 by 2, we would land at -1, -2. And so on. Are we kind of getting that, you guys? And then from the other equation I wrote, which has the same graph, the difference is I would read this as being a vertical stretch or compression. Stretch by a factor of 2. And that's because we're thinking about multiplying each y from the parent function by 2 to have the same x value as the parent function. Zero, 0 wouldn't go anywhere, but like if we think about, 1, 1, and then we multiply the y value by 2, 1, 1 would then go to 1, 2, exactly. 2, 2 would go to 2, 4, exactly. 3, 3 would go to 3, 6, right? So it's just, you're multiplying each of the y values in order to have the same x value as the parent function. Okay. Now, I have mentioned this already, the standard transformation form. Okay, but basically, if you get your equation where you can identify what the parent function is, and then think about the equation as being a result of transformations being applied to a parent function, if you get your equation into this form, you can think about reading from left to right and applying the transformations in that order, and they'll always be applied in the correct, like your graph will always be correct. Now, we were talking about doing shifts before, and like if there's just a horizontal shift and a vertical shift, like it doesn't actually matter like which shift you think about applying first. I am highly recommending that you think about applying like a horizontal shift before a vertical shift. And part of that is because if there's any sort of like reflection with the shift or dilation like with the shift, you could potentially end up with the wrong graph if you apply in the wrong order and like don't take into account like that your axis that you're rotating about or reflecting over has changed. So like looking at this, thinking about going from left to right and thinking about what each of these values might do, like A would result in there either being a vertical reflection and or a vertical stretch or compression. B would be a horizontal reflection and or a horizontal stretch or compression. C is the horizontal shift, and you can see that whatever x was being multiplied by has been factored out in this form. And then D would be the vertical shift. Right, and the horizontal shift will be left, right, or right. The vertical shift would be up or down. Okay, so given a parent function, let's go ahead and come up with the equations that would represent the new function that's created from applying these transformations to this parent function of x squared. So maybe this first one I'll call w of x. Okay. So for the parent function to then have a vertical stretch by a factor of 4, how would we write that?
Vertical stretch by a factor of 4. So we go g of x equal to.
Well, I'm creating a new equation, right?
Oh, sorry, w of x is equal to 4 times x squared?
Yeah.
Your time.
Okay, horizontal, sorry you guys, I'm just getting a message from my mom. She has my daughter right now. Okay, horizontal compression by a factor of 2. So why don't I call this, I don't know, P of x? Horizontal compression by a factor of 2, how would we write that? As an equation. Horizontal, so it's happening to the x. So it's going to be inside the parentheses here. And x would be multiplied by 2. Notice, you guys, that 2x squared is the same as 4x squared. Like, these graphs would be the same, but it's from a different perspective that you would think about graphing them, right? Like, this would be a vertical stretch by a factor of 4, multiplying all the y values by 4. This would be horizontal compression by a factor of 2. So you're thinking about dividing all of the x values by 2 to have the same y value. They end up being the same. Okay, we're getting a little complicated here. More transformations happening. Okay, reflection about the x-axis. A vertical compression by a factor of 3 and a shift to the left 1. Do you want to take a second and think about it? Write down what you think it would be. A reflection about the x-axis. So vertical reflection, vertical compression by a factor of 3, and then a shift to the left 1. Is your hand up again? Do you want to share your answer?
I put equal to 1/3
Okay.
times
Okay.
times parentheses
Okay.
x
Okay.
plus 1 parentheses squared on the outside.
Okay. So I see the vertical compression by a factor of 3 and the shift to the left 1.
Oh,
What about the
minus
reflection?
Yeah, minus x, right?
A reflection about the x-axis would correspond to a horizontal or a vertical reflection,
Vertical.
which means we would write this
Minus
as
on the outside.
minus 1/3. Yeah, this could also look like if you wanted to put the x plus 1 squared in the numerator and then the 3 in the denominator, it could also look like that. I'm all thrown off. What time does the period go to? Is it 30 something?
Yeah, 37.
37?
You got that.
Okay, cool. We're doing great. All right, horizontal stretch. So why don't you guys try this one? Horizontal stretch by a factor of 4, shift to the right 2, and then a shift down 5. Horizontal stretch by a factor of 4, shift to the right 2, down 5. I'm going to call this, how about T? I already did Z. T of X. Okay, go ahead.
1/4, sorry, open. 1/4, open. X minus 2, close, close, minus 5.
Close, close. Minus, oh, squared. Minus 5. So horizontal stretch by a factor of 4, multiplying by the 1/4, the x. Okay, shift to the right 2, down 5. Looks good. Are we okay with that? Are we okay with that? These ones are tricky. Like practice of doing these, and I definitely encourage, especially the ones where you're just having to figure out what the graph is, write out the transformations. Think about what the list would look like of the transformations and in order. Cube root of x is our parent function, sideways chair. Let's go ahead and graph our sideways chair. So I think about the point 0, 0, 1, 1, negative 1, negative 1. And then if you want to, you could do 8, 2, negative 8, negative 2. Okay, so our parent function f And how would we describe what that 2 is doing to the parent function? Cube root of x. What is that 2 doing?
2.
It's being a 2. It is being a 2. Is it vertical or horizontal? Vertical. There we go. We're acting it out. You guys said vertical. I started writing horizontal. So it's a vertical. Else did the motioning. A vertical stretch. I am picky on this. Write out vertical stretch by a factor of 2. Different math texts, you guys will end up describing dilations in different ways. This is like, I feel like makes the most sense, at least to me, so I teach it this way, and you guys have to do it too. Our department does it this way.
Argue?
You're gonna argue?
I had a way that another teacher used for a while, which was that she said dilation, right? Just everything will kind of be a dilation, and then if it's 2, it's for specifically like in vertical. If it's 2, it's a stretch, and if it's a fraction, it's a shrink. So we just keep dilation, but then it's 2.
You wouldn't describe.
Yeah,
you wouldn't say stretch.
Yes.
Or you would just be using the factor, like saying like, oh, the parent function, like the y values are being multiplied by 2 or 1/2.
Yeah.
Not wrong.
It's not wrong. I get very confused by vertical shrink by 1/2 because that would mean that's also.
Well, I wouldn't say that.
Yes.
I would say a vertical shrink by a factor of 2, and you know because you see vertical, it's happening to the outside of the function. Because you see shrink, you know you're thinking about dividing each of the y values by 2. Right? Versus stretch, you're like, oh, I'm multiplying. Okay. And then let's graph it. So let's think. Let's multiply each of the y values by 2. So 0, 0 wouldn't go anywhere. 1, 1 would land at 1, 2. 8, 2 lands at 8, 4. Okay, -1, -1 lands at -1, -2. -8, -2 lands at -8, -4. Gee. All right, h of x. We're getting a little more complicated with each new function. H of x, reading from left to right, that negative indicates read that. What's the negative indicate? It's vertical reflection. Good. And then Regan, what would that 2 be doing?
That 2 would be horizontally stretched.
Horizontally compression. Yeah, it's a horizontal compression. Or I'm cool with you saying shrink. If shrink helps you like visualize it better, I'm okay with shrink. Horizontal compression by a factor of 2. Okay, so then taking each of those points from the parent function through that, 0, 0 stays there for the reflection and the compression. 1, 1 reflects to be at 1, -1. And then when we compress by 2, we land at 1/2 -1. 8, 2, we reflect to be at 8, -2, and then when we compress, we are at 4, -2. You could think about taking each of the points, or you're like, oh, I know like what the basic shape should be, right? Like, so like -1, -1 reflect, And then when we multiply, when we divide 1 by 2, we would be at 1/2 1. Okay, and then -8, -2, reflecting over the x-axis would put us at -8, 2. And then we'll be at -4, 2 after the horizontal compression. And then this last one here, we have a little bit of work to do before we can actually think about graphing. So because x is being multiplied by -1, we need to think about factoring out what x is being multiplied by, because we also want to be able to see the actual horizontal shift. I'm also going to think about rewriting this as 1/2 times the cube root. You don't have to do that. Of -1 times the quantity x minus 3. That just helps me with reading from left to right. Where that 1/2 I interpret as being a vertical compression. Perfect. By a factor of 2. That negative on the inside of the radical would be a horizontal reflection. And then the -3 will be right 3. And let's think about taking our points from the parent function through that list. Okay, so vertical compression. So dividing the y-coordinate by 2, it doesn't matter for 0, 0. Horizontal reflection does nothing. And then we're going to shift to the right 3. That's 4. Right 3. The point that's at 1, 1 would go to 1, 1/2. Horizontal reflection would be at -1, 1/2, and then right 3, 1, 2, 3. Okay. Sometimes you can just think about like dealing with the point that's at 0, 0, and then kind of creating the graph from there. So, some of the more complicated ones, I have to like think about going through the entire list for all of those common points. So like vertical compression by a factor of 2 for at the point 8, 2 would lead us to 8, 1. Horizontal reflection, we would be at -8, 1. And then right 3 will be at -5, 1. Okay, taking -1, -1, or applying a vertical compression would be at -1, -1/2. Horizontal reflection, I would be at 1, -1/2, and then right 3, 1, 2, 3. And then -8, -2 lands at -8, -1, reflecting across the y-axis, lands us at 8, -1, and then to the right 3, 1, 2, 3, I would be off of the graph. For J. So this is where we will stop. You guys have a little bit more practice from the textbook on that now will include dilations. And then next class, we're gonna kind of put it all together. You'll have time to like do more practice next class. And then if you noticed, I put your next quiz up for next Friday, because I won't see you guys until Wednesday. I won't see you on Wednesday. Oh no, that's not next week. The week after, you guys have PCT coming up, and I'm missing seeing you guys on like a Tuesday, or maybe it's not you guys. I can't remember. On the 8th, PSAT. Anyhow, I will see you next week. I'll see you next Wednesday. And then you guys will have a quiz on section 1.3 on Friday.